Okay, now we can go ahead and make the calculation, and we find ultimately that K is equal to what? So, let's see. So 1404 divided by parentheses 298 times 0.0083145. Wow. So this part of it up here works out to 566 or thereabouts, right? Okay. That's because you have a solve function. Oh. Did you get an actual numeric answer?
Yeah.
What is it?
It's massive.
1.238 times 10 to the 246.
That's probably about right. Well, if you're looking for a K for this, what did we say about from the test the last time? What did we say about the K value for something that was soluble? It would be very large. What do you think the equilibrium constant is for a reaction that goes to completion? Also exceptionally large. This calculator won't even give me a number to go with that. I typed that in there and it spat out overflow error. It's too big a number for this calculator to deal with. So K equals approximately 10 to the 200th.
So it's exceptionally large.
It's
than equilibrium.
yeah. It's very, very, very large. Which, you know, this reaction goes to completion, so we ought not to be surprised by that. So that kind of brings up the idea, does an equilibrium for a constant, or an equilibrium constant for a reaction that we know goes to completion, does it make a lot of sense? Probably not a great deal. It's okay. All right. Now for the new stuff. Chapter 17, Electrochemistry. The last chapter of new material. We have a couple of chapters to go through after this, but it's all basically a rehash of stuff from honors, just in a little more detail. We will blow through it very quickly. And we're going to spend a day, May 7th, at 8 o'clock in the morning, as I recall.
It's like a lab.
Might be 7:30.
Is that like a...
Actually, sorry about the tangent. 8 a.m. local time, Monday, May 7th. If you haven't paid your fee yet, please do that.
Well, I did
Register for it.
tonight.
Okay, so electrochemistry. The first question we can ask is, what is it?
The electronic.
What is electrochemistry? And the short answer is, it is the relationship between chemical energy and electrical energy. And this is a useful sort of thing to be able to do. without electrochemistry, there are no batteries.
Yeah.
And without batteries, there are no solve functions or cell phones or iPads recording lectures for people who are on a jacuzzi trip.
Jacuzzi party.
Yes.
What's it called? The jacuzzi party.
Well, that's what the man calls it.
I-
It's okay.
The man is George Washington.
All right.
Why did we start calling him?
That's exactly what I was thinking.
Just lucky, I guess. Okay,
Lucky
Because
for
there's
him.
like
Let me-
1 billion.
let me suggest that there is one other way that we could define electrochemistry. We can also define electrochemistry as the practical application of redox.
We didn't learn that.
So, all that stuff we learned about oxidation reduction back in chapter 4, we are going to resurrect and put to use now. Okay? Let me show you a typical, very common in fact, oxidation reduction reaction. And one that we've even gone through together, as I recall. That's a skeleton equation that is not balanced. Okay? Now, is this a redox equation?
Probably.
Other than the
Yes.
context of the conversation,
Yes.
what would tell you that it is?
Lead gets reduced, oxidized.
Okay? So, the fact that we have a pure element involved in a reaction, that's a pretty good sign of what we're dealing with as redox. Okay? Now, when we are faced with a redox situation, what is the easiest way to approach it?
Half reaction.
2 half reactions. Okay? So, 1 half reaction would look like this. That's 1 half reaction. Another half reaction would be that. Now again, neither one of these is a complete reaction yet. These are places to start. How do we determine which one is oxidation, which one is reduction? Well, the easiest way to do that is to go back to the original equation and determine oxidation states. What's the oxidation state of lead? 0. Why?
Because it's a pure.
Because it's a pure element. What's the oxidation state of this lead?
Plus 4.
4 plus, yep, plus 4. Plus 4. Oxygen, of course, is always -2 unless it's peroxide. No reason to suspect that that's peroxide.
And there's P.
Hydrogen? Really?
Plus 1.
Plus 1, it's an acid. Hydrogen has to be positive. SO4. Well, if oxygen is always -2, that's a total of -8. Offset by 2 plus 1, so sulfur has to be +6. Now, since we've got the same ion over here, we know that those two numbers don't change. And what is the condition of lead here? What is the oxidation state? +2. Okay? So, in this reaction, we have lead 0 going to lead +2. Does this represent oxidation or reduction? This is oxidation. Okay? And this one, we have lead +4 going to lead +2. This one is reduction. Okay? Now, neither of these is balanced. We can go through and we can write the balanced equation for each one of these based on the rules that we talked about back in Chapter 4. We're not going to do that at this time. But it is useful to identify which process is going on where.